Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Thank you, Atia, and thank you. Congratulations to Dr. Nick and his team for organizing this event, and also thank you for inviting me to share some of the work that I have done during the past 10 years or so regarding these nanoparticles. When Dr. Nick suggested to me to give a talk on chemistry of nanoparticles, so there are two things that worry me. First is the time allocated is half an hour. In fact, this is a one semester course that is being offered in the Department of Chemistry for the fourth year undergraduate. And second is the audience, maybe not all are chemistry majors. Okay, so I will try my best to give not too deep in the chemistry theory or the principles. Okay, so maybe at the end of the lecture, I'll give you a quiz. Okay, right. So chemistry of nanoparticles. So let's begin with. So I've arranged my presentation into these topics. So I will give a brief introduction. What is nano? And then why we are interested in nano-sized material. Okay. So what are the properties? Okay. When we compare to bulk-sized material. Okay. And then as chemists, so we are more concerned about the synthesis method to prepare, because not every sample you can buy from supplier. And also if the material is available, but maybe not to our needs. Okay, so we need to synthesize in the lab. So this is where the fun, okay, takes place. Okay, so when we talk about synthesis, so there are several aspects that need to be considered. So nucleation and growth, because we want to limit the size of the particle. So we want it to be in nano size. Okay, so we have to understand the nucleation and also the growth of the nanoparticle. Okay, so this is a the kinetic process that occur in the during the synthesis. And also we need to understand how to stabilize. Okay, so some nanoparticles after several days or several months, maybe they change their size. Okay, so we need to stabilize them so we can keep them for long time. Okay, and finally I will touch on this is more direct or more related to the seminar. It's a bioreduction. Okay, where we use plant, okay, part of the plant to synthesize our nanoparticle. Okay, so basically what is nano? I think maybe we have heard this many times. So nano is just a scale, right? So 1 nanometer means 10 to the minus 9 of meter. So that is the scale of the things that we are talking about. So nanoparticle maybe consists of 1 nanometer, maybe 3 to 5 atoms. So it's very, very small. Okay, right. So you can compare. So nanochemistry is not a new thing, because in nature you have this DNA also nanosized, nanosized compound, things like that. So even red blood cells or maybe virus. Okay, so we can do the comparison. Okay, so in terms of the size, right? So why we are interested in nanoparticle or nanoscale material? Because the properties are very different from bulk size material. Okay, so these new properties will lead to new technologies. Okay, so that's why we are interested in nanoparticles. Okay, so materials that can exist in nano size. Okay, right. So there are two reasons why these properties change very differently because of the increase in the surface area to volume ratio. Okay, so the smaller the size, the higher the surface area. Okay, right. So and then secondly, we cannot use classical physics law to explain these properties. So we need to go into quantum physics. So because of these two phenomena, so the properties will be very different. Okay, so I will show some examples where increased surface area to volume ratio will lead to different properties and how the quantum confinement or quantum size effect explain the new properties of nanomaterial. Right. Oh, sorry. I don't like to use this because you can see I'm shaking. Yeah? Right. Okay. So nanomaterials, they have a larger surface area. So when compared to the same mass of material produced in the larger form. So that means the smaller the particle, okay, right, the higher the larger the surface area. So compared to the volume, okay. So this will lead to more chemically reactive, okay. So and then it will enhance their mechanical strength and also the electrical properties. Okay, so how to explain this? We need to go back to the physics. Okay, for example, the mechanical strength, okay, Young modulus, the electrical properties, Ohm's law. Okay, so how we can explain this nano size material? The conductivity is very different from bulk size. Okay, and second is the quantum size effect. So this quantum size effect begin to dominate when you have matter at nanoscale. So as I said, we cannot use classical physics. Okay, so we need to use quantum physics to explain this behavior. Right. So let's see. So the first phenomena is larger surface area to volume ratio. Okay, so right. So I show you here. Okay, so this is the dimension is larger than when compared to this cube because you cut into smaller size. So you can do very simple mathematics. So you can calculate the surface area and then divide by the volume. So you can see here as the size of the cube becomes smaller, you get higher surface area to volume ratio. Okay, right. So how this affect the properties? Because you have more surface atoms. Okay, so you have more surface atoms, and surface atoms, atom at the surface, they are very active. They are very reactive. Okay, right. So because of they are very reactive, more you have more surface atoms. So that means they will show better catalytic properties. Okay, or as absorbents because you have more materials that are exposed for the reaction to take place. So because catalyst is a surface, okay, surface phenomena, so you have more surface atoms, so they will make it better as a catalyst. Okay, right. Second is the quantum size effect. Right. So as we go from left to right, the size is decreasing. Okay, right. So as the size decrease, now the band gap. So the band gap is the energy difference between your valence band and conduction band. Okay, right. So this is more for semiconductor material. Semiconductor material. So when we want to explain the optical properties or the electrical properties, right? So the band gap will start to increase. Okay, as the size become smaller. Okay, right. So the confined electrons have higher energy. Okay, so the confined electron. So here the electrons are free to move from the valence band into the conduction band. Okay, because the energy difference is small. But as the energy gap becomes larger, so the electron is confined. Okay, right. So this explains why the electronic and optical properties differ from those of bulk material. Okay, because of the difference in the band gap. Okay, right. Okay, so we can use that, okay, to explain the optical properties of gold nanoparticle, right? So luckily, nanoparticles such as gold and silver, they will show what we call surface plasmon resonance. So you can run simple UV and it will show you absorption in the visible region. Okay, so visible region means between 400 and 800. Okay, right. So this is what we call surface plasmon resonance. Right. So this is one of the characterization technique or method to show that you can monitor the formation of nanoparticle. Okay, right. So you can see here. So as the size changes, you get different color. Okay, so different color means it absorbs different wavelength of light. Okay, right. So what is more important, I always tell my students, okay, so look at the position of the lambda max. So the tip of the band. Okay, so that tells us the size of your nanoparticle. Okay, so we can say here, so as the size increase or as the lambda max go to longer wavelength, you get larger size. Okay, so during your synthesis, maybe you can use this position of your lambda max to monitor the size of the nanoparticle. Okay, right. So if the lambda max shift to the left to shorter wavelength, so that means you are going to much smaller size. So if size is what important criteria for your needs. Okay. Right. So if size does not matter, then it's okay. Right. Right. I think for medical application, for example, gold therapy. So I think they look for bigger size, because of the lower energy. Okay. Right. So that's what people told me. So if it's good if you can have blue gold. Okay, so gold in showing blue color means longer wavelength but less energy. Okay, right. Okay, right. So that is one. Okay, size also or the shape also will affect or influence the optical properties. So So for silver nanoparticle, right? So different shape of nanoparticle will give you different color. Okay, right. So how to get this prism or triangle or nano rods? Okay, so this is where we need to do the synthesis to understand the synthesis. How can we control the size and shape of nanoparticle? So a lot of parameters that need to be considered Okay. Right. Um, okay. Right. So just to finish off about this introduction, so smallness leads to new properties. Okay. Right. For example, we take aluminium. Bulk aluminium is inert. It's inert. But when you have nano aluminium, it start to become more reactive. So it can catch fire and cause explosion. Okay. Right. So gold. So if we look at gold, bulk gold, okay, is also inert. So the ladies, they wear gold jewelry. Will not undergo oxidation. It's inert. But when you have nano-sized gold, it start to become oxidation catalyst. Okay, can use as catalyst. Okay, right. So that means size, the size, the nano size will lead to different new properties. Okay, right. So synthesis. So I will just briefly touch on the synthesis. Letak this one. On the synthesis part. Okay. So why the synthesis? Because this is where we use our skills, okay, to design, okay, what we require. For example, if you want a catalyst, if you want to use as a catalyst, so there are some aspects that need to be considered. You need high surface area, okay, things like that. The size or maybe the shape. Okay, so designing and preparing nanoparticles with high functionality using specific method. Okay, so that is the idea of synthesis. Okay, right. So here, during the synthesis, so it will involve the size control, the shape, okay, the structure, and also maybe the purity. Okay, so we don't want the nanoparticle to be contaminated. So it will affect the final properties later on. Okay, right. So in the synthesis technique, okay, so there are two approaches, either top down or bottom up. Okay, right. And then the kinetics, the growth kinetic. So we want to understand about the nucleation and growth, and also stabilization. Okay, so these are the things that we need to consider during the synthesis part. Okay, right, top down and bottom up. Okay, so if you top down means you start from small, okay, and then build up. Okay, so in top down, so from large into small. Okay, right. So okay, right. So nucleation and growth of nanoparticles. So during the formation of nanoparticle, right, it must follow or it must undergo two-stage process. So first, it will undergo nucleation and then followed by crystal growth. Okay, so you must be able to form a nucleus first. So this is the point where you start growing. You start growing. So nucleus can be considered as a seed. Okay, macam benih. So that dia boleh membesar. Okay, right. So if we can understand this nucleation and growth process, so we can improve the synthesis method. Okay. So for example, nucleation is where it will affect the morphology. Okay. So the rate of nucleation will affect the size and the shape of your final product. Okay. Right. Right. For example, so if you have fast nucleation, okay, you it will lead to small nanoparticle. Right? So you have a very fast nucleation, so it will lead to small nanoparticle. So in contrast, if you have very slow nucleation, so you get large nanoparticles. Okay. So for example, if you use reduction technique, so fast nucleation means you need to use strong reducing agent. Okay. If you use reduction technique, okay, I will show later. So if you use chemical reduction technique or bioreduction technique, so your reducing agent must be very strong in order to get fast nucleation. Okay, right. So if your reducing agent is weaker or weak, so you get very slow nucleation, and normally it will lead to large nanoparticle. Okay. Okay. So another mechanism, right, that will affect the size, the growth of nanoparticle is what we call Oswald ripening. Okay. So Oswald ripening is something, is a kinetic. Okay, it's a kinetic effect. So whereby in your sample you have different size of particle, large and small. So it undergoes Oswald ripening, so the large particle will eat up the small particle. Okay, so the small particle will, we call, dissolve into the large particle. So on average you have large particle, because the small particle being eaten up by the large particle. So that's why I don't encourage my student to stir during the synthesis, because when you start stirring, so you increase the collision process. Okay, so you increase the collision process, so it will increase the ripening growth. So just leave it on the bench until it will completely reduce. Okay, so you, if you start stirring, so it will undergo collision. Okay, so increased collision means you get more chances of Oswald ripening. Okay, right. So however, this Oswald ripening can be stopped. Okay, so we can stop Oswald ripening. Okay, even if you don't stir, because the Brownian motion in the sample. Okay, so, right. So collision will always take place in Brownian motion. Right. So you can stop this Oswald ripening by using stabilizer or capping agent. Okay. So this stabilizer or capping agent will limit the size of the nanoparticle. Okay. Right. So it will restrict the particle growth. So when you use capping agent, so that's why in the synthesis you must add something as your capping agent or stabilizer. Okay. Okay, right. So why we need to stabilize or cap this nanoparticle? Because we want it to be monodispersed. So we have a uniform size, uniform shape. Okay, right. So, and also we want to avoid agglomeration. Okay, so the growing of the nanoparticle. Okay, right. So example of stabilizer or capping agent, you can use surfactant molecule, C-type or STS, Triton X, all these are surfactant molecules. Or you can use polymers, PVP, PVA, PEG, etc. Or maybe some organic molecules, oleic acid, citric acid, glucose. So you can use this compound as capping agent of stabilizers. How how good are they? We need to evaluate. Okay, right. Some are very good, but some are not so good because the capping is quite loose, very weak. Okay, so when we talk about monodisperse, we want to have a good sample like this. So uniform size. Okay, and then there are not lumped together. So agglomeration, you get something like that. Okay. So this is a good sample, okay, compared to that one. So of course, people say agglomeration can be overcome by ultrasonic. It's okay. Right. Before you send for the TEM analysis. Okay, right. So other parameters for size and shape controls include the concentration of your metal ion, and also the capping agent, the stabilizer, and then the relative concentration between these two. Maybe reaction temperature, okay. So when you start heating up, okay, and then time, okay, how long you have to wait before you start collecting your sample, or maybe solution pH, okay. So these are parameters that you can always vary in order to get size and shape control synthesis. Okay, right. So for example, effect of reaction pH here. So at different pH, the size of the nanoparticles are different. Okay. So in fact, addition of salt, for example, NaCl, also can change the size of your nanoparticle. Okay. Right. Okay. Right. Okay. Stabilization. There are two approaches. Either we use electrostatic or steric. Okay. So most common is the steric. Steric polymerization, stabilization. Okay, let's see. This is electrostatic. So you have ions. So under electrostatic stabilization, so you have ions absorbed on the surface of your nanoparticle, and this will create electrical, what you call charge. Okay, electrical charge, and so this electrical charge on your nanoparticle will create what we call electrical double layer between these two neighboring particles. Okay, between these two neighboring particles, and because of the same charge, so it will repel. Okay, so it will repel means this particle cannot come closer to that particle, because of the electrical double layer. Okay, right. And for steric stabilization, so this is where you add polymers, surfactant molecules. So these surfactant and polymers, they are large molecule, okay? So they will absorb on the surface of your nanoparticle, and because of steric hindrance, when the two particles comes closer to one another, right? So because of the polymer molecules, it will restrict. You have a barrier, okay? A potential barrier where you cannot get close to one another. Okay, right. So this is where how stabilizers such as surfactants, organic molecules, polymers, uh, restrict the particle agglomeration. Okay, right. So this is a summary. So if you don't do stabilization, you get large size or you get agglomeration. But if you do stabilization, you get small size. Okay, right. Okay, so there are many methods that you can choose to do your to synthesize your nanoparticle. So it can be a physical method. Okay, for example, mechanical milling. So if you have the instrument, you can use that technique. Okay, or you can use for example, physical vapor deposition technique also can. So if you have the machine, if you have the what you call this facilities, you have the skill to perform this synthesis is up to you. Okay, right. So second is the chemical method. Okay, so gel, CVD, colloidal is a chemical reduction. Okay, chemical reduction technique. And recently, okay, maybe 10 to 15 years ago, people have suggested using biological method. Okay, so under this biological method, because it's considered as green techniques, okay, either you use microbes, bacteria, or you can use biomass. For example, part of the plant, the leaf, etc. etc. Okay, right. So I'm going to choose one method, okay, the colloidal method, okay, and then I will follow with the biological method, okay, right. So why I choose this colloidal method? Because this is the beginning, okay, the bioreduction method follow the chemical reduction method, okay, right. So the difference is the type of reducing agent. Okay, so under colloidal or chemical reduction technique, okay, so you must have a precursor, okay. So the precursor here may be a metal salt, for example, metal ions, silver plus or gold 3 plus, okay. And you must have this capping agent or reducing agent, okay. And to do the reduction, you need a reducing agent, okay, right. So you can heat if needed, okay, or you can stir if needed, right. Right. So I prefer to do it room temperature and just leave it on the bench. Okay, right. So you get this, your nanoparticle. Okay, right. So reducing agent can use sodium citrate, sodium borohydride, ascorbic acid. Okay, right. So these are some examples of reducing agent, chemical reducing agent. So your capping agent can be thiols, okay, the sulfur compound, your citrate, or maybe polymers. Okay, polymers such as polyvinyl alcohol or polyvinyl pyrolytic. Okay, right. So you need three things, right? Your metal ion precursor, your capping agent, and your reducing agent. Okay, right. Right. So this is the original method of chemical reducing technique. Okay. So they call it Teknologi method. I think 1950s something. Okay. Right. So what he did, okay, what Teknologi reported. So the precursor, this is for gold nanoparticle. So he used chloroauric acid as the precursor. Okay. At 80 degrees Celsius. Stir. Okay. Right. And then add sodium citrate. Sodium citrate is the reducing agent. Okay. Right. And at the same time is the stabilizer or capping agent. Right. Continue stirring. 2 minutes. Okay. So you get color change from clear solution, or maybe pale yellow to gold. Apa color dia? Hati-hati. Red, some red, okay, red color, so you get red color. So mix them together, bacalah Bismillahirrahmanirrahim, okay, you get color change, okay. So this is this color change, okay, indicate the formation of gold nanoparticle, because the SPR band, okay, the SPR, okay, right. So if there is no color change, that means it doesn't work. So this color, the change in color, tell us that the nanoparticle is formed. Okay, because gold, what you call this? Gold atom, okay, gold zero, has no absorption. But in size, in nano size, it will show absorption. Okay, SPR. Okay. Right. Okay. So citrate stabilized gold nanoparticle is not very stable. It's not very stable. Okay, because the citrate capping is very loose. Because to a sample of gold nanoparticle solution, if you add sodium chloride, right, you can see color change from red to blue. Okay, so from red to blue means increase in size. Okay, you see, right? So this is the A, red, and this is blue. So the position of the lambda max now from short to longer wavelength. So longer wavelength means increase in size. So that means you disturb the citrate stabilizing. Okay. So you disturb the what you call this, you destroy the protecting layer. So when you destroy the protecting layer, the particles now can agglomerate. Huh? Okay. So that's why citrate is not a good stabilizer. Okay. So we can show in the lab that when you add sodium chloride, so you can see color change from red to blue. So that means the size of your nanoparticle now has increased. Huh? Okay, right. Okay, right. Okay, so now after we understand the chemical reduction technique, so now we go to the bioreduction. Okay, so in bioreduction, the same thing. You need a precursor, metal ion precursor. You need a stabilizing agent, and also you need a reducing agent. Okay, right. Okay. So why we need to use this biological method, because we want to avoid using chemicals, right? So we want to avoid using toxic reducing agents such as sodium borohydride, chemical stabilizer like polyvinyl alcohol, things like that. Okay, right. So for I think for biological application, so you need to use compound that are biocompatible to the body system or etc. Okay, so advantages of using biological method. So you can do at room temperature. So no toxic solvent involved, no expensive equipment, and is environment eco-friendly. So however, the disadvantages, so the mechanism. Okay, so mechanism sometimes cannot be understood. Okay, and you get mixture of shape, because when you use, for example, plant extract, there are so many biomolecules inside there. So there are so many potential reducing agent inside there. So you can get various shapes. Okay, various mixture of shape, and also reproducibility. So today you do the synthesis, after 1 month you try to repeat, maybe you get different set of results. Okay, right. Okay, right. So this is just why the motivation to do this bioreduction technique is because of we care about the environment. The green chemistry principles. So avoid using toxic chemicals or byproducts, things like that. Okay, right. Uh, right. Some examples of biomolecules from plant extract. Okay, so these are some examples only. There are many more. Okay, so I cannot put all them in the slide. Okay, right. So for example, gallic acid. So gallic acid, fumaric acid, myricetin, quercetin. Okay. So look at the one that I circle. That is the active part of the molecule. Right. So the active part of the molecule. Okay. So this is where people propose the mechanism of electron transfer. So these are the potential reducing agent. Okay. To reduce metal ion, and this compound will be oxidized. Okay. So people say that these are antioxidant. Okay. So antioxidant molecules, or molecules that lead to the antioxidant properties of your compound. Okay. Right. Okay. So this is the mechanism. Okay. Right. This is a proposed mechanism. So look at that OH. To the two OH group. Right. So it will transfer electron to your metal ions in the two-step process. And then you form this final product. Okay, right. So this is just a mechanism being proposed. So the exact mechanism, I have no idea. Okay, right. Okay, right. So the bioreduction process, as I said to you, is to monitor using UV, right? So if you have a peak in your UV, right? So that means you being successful to form a bioreduction process. Right. For example, your precursor has no absorption band, your chloroauric acid, and this is the leaf extract, but this is the nanoparticle. You have a band. So you can monitor, okay, by using UV. Right. And then you can send your sample, okay, just to prove the biomolecules acting as reducing agent and also capping agent. So do IR, okay, do IR and then compare between your leaf powder, for example, and also your nanoparticle sample. So it will show similar pattern. So similar pattern means the biomolecules are on the surface of your nanoparticle. So that means other than reducing the metal ion, it will also acting as capping agent. Okay, right. Okay, right. So we submitted one paper to a journal, and the referee asked to prove. Okay, so not enough by using IR, so we send for cyclovoltammetric analysis. Okay, right. So this is where we prove, right? So oxidation, okay, cyclovoltammetric means you have oxidation and reduction process. So the forward is oxidation and the backward is the reduction. Okay, right. So this is the oxidation from A to B. So this is A, right? This is the peak, and this is B. Okay, right. So for the gold sample, okay, so get this back reduction means B back to A, right? So that means in the reduction, in the bioreduction process, sorry. Oh. So that one changed to this group, okay? The OH changed to this C double bond O and C double bond O. The catechol to quinone structure, right? And then for the gold nanoparticle sample, we prove that B now back to A. So that means the capping is the capping the structure of the capping compound is that one. So that means it's a reverse. Okay, it's a reverse. It's a reduction, oxidation. Okay, right. Okay, right. So this is just a reminder. Those using plant extract, maybe you get maybe you don't get single peak in your UV, maybe you get more than one peak. Right. But always remember that peak must be in the visible region. So the visible region means the SPR. Okay. Outside that visible region, it may cause, it may arise from other compound. Okay. Right. So this is where we use daun kantan. Okay, daun kantan. So we get two SPR band, right? One at about 530 and another one at about 700 nanometer. Okay, so it tells us that maybe a mixture of shape. A mixture of shape. Okay, so to confirm it, so we send for TEM. Okay, and TEM showed that other than spherical, you get triangle, you get other shapes. Okay, so you get triangle there, you get this hexagon, you get this cubic, what things like that. So that means if you have more than one SPR band, okay, so you get a mixture of shape. So that is a problem with plant extract. Okay, right. So can it be avoided? Yes, by doing some modification in the parameter, in the synthesis parameter. For example, change the pH. Okay, right. Okay, controlling the synthesis parameter. Okay, I'll go very quickly. Right. So look at the concentration effect. So again, look at the position of the lambda max. Okay, so don't, let's see, how can I say, jangan terikat sangat dengan literature report. So you have different plant extract. Maybe your plant extract behave differently. Always look at your own result. So look at the position of your lambda max. Kalau dia anjak ke kiri, that means small size. Dia anjak ke kanan, large size. Itu saja. So as I said, different plant extract will give you different results. Okay. So in fact, we tested one plant last time. One we obtained from Johor, the other one we obtained from Kelantan. Different, walaupun pokok yang sama. So I don't know, maybe you people from biology can explain why different species, or I don't know, different species or different constituent in the plant. Okay, right. Always look at the position of your lambda max. So when you increase, for example, the concentration, if it shifts to the left, that means you are decreasing the size. Okay, so or it shift to the right, to longer wavelength, you are increasing the size. Okay, so this is one parameter that you can change. pH also, you see, pH. So if you change the pH, for example, in this case, you lower the pH. So if you lower the pH, you get shift to the right. So that is telling at lower pH, size increase. Okay, right. So it all depends on your own plant extract. Okay. Okay. So right. So why different pH will give you different size? Because you modify the structure of your biomolecule. You modify the structure. So, for example, at lower pH means you are adding H plus. Okay, so you protonate that OH group. Okay, right. So at higher pH, you are adding OH minus. So you remove the hydrogen from the OH group. And this is a better capping agent. Eh? So the O minus is a better capping agent, right? Compared to the OH, right? Okay, right. And temperature also, so you can play around with the temperature. So always, again, look at the shifting of your SPR band. Eh? Okay, right. So when you influence of temperature is regarding the nucleation rate. Eh? So you give energy to the system. So maybe fast nucleation or slow nucleation. Eh? Okay. Right. So I think that's all. Eh? Today. So thank you very much for your attention.